Me again, reporting from a new and seemingly completely blank location. But don't be worried, it'll still be fun. Probably. Today we're going to talk about the autocomplete assignment. You guys use autocomplete all the time. Google makes you use it, in fact, when you're on their website. So I might type, for example, what? And Google comes up with the things that are most popular right now. You can see this is going to be a dated video in a hurry, but WhatsApp was just sold for an insane amount of money. Here we see a number of other very 2014 topics. And of course, as you type, Google will keep looking to see what the most common things are. So I could maybe do what is the deal with? And these are the four most popular queries at the moment. Again, what does the fox say? So of course, there's a lot of cool things you could discover with autocomplete about the proclivities and thoughts of the masses out there. But we don't want to rely just on Google for our data sets. We'd like to be able to do things on our own. So on this assignment, you're going to build your own autocomplete data structure that will allow that kind of query on arbitrary data sets. We're going to provide you a GUI you can use, and your autocomplete data type will be the engine that will allow you to probe. For example, here I have a list of movies, and I might say, okay, what's the highest grossing film that starts with Planet? Oh, well, it's Planet of the Apes. Yeah, makes sense. Less popular, Planet Bouncy, and so forth. And your data type is going to have to be sufficiently fast that it can support this real-time interaction with the data. By now, you're no doubt hungering to build your own autocomplete data structure. Well, hunger not, for it's actually a fairly simple idea conceptually. So let's start by just looking at the data set. This is what we provide. Data sets like this. It's plain text. There's around 230,000 movies in this database. And at the very top, we see Avatar, which earned $760 million in the US. And as we scroll down, we see movies that earn less money. Now, given a plain text file like this, you might say, well, how do I find the movies that start with Planet and sort them by how much money they made? So a very natural approach is to take the data file and sort everything by the names of the movies, and then binary search to find the earliest thing that starts with Planet, the latest thing that starts with Planet, and then just return these as one big array that you can then sort by the weight, or the earnings in this case. This assignment, while conceptually quite simple, has a number of tricky Java syntax issues, chief among them being the comparator. But it's going to turn out to be a really, really beautiful abstraction that's going to let us do something you probably would have never thought of doing on your own programming. So here is the main class that we're going to build first, called term. Each term is going to correspond to one line in our data file. So for example, here's one line of it. It consists of a string and a weight, which we call a query and a weight. Now, in addition to containing the information from our data files, we'll also have a number of comparison methods that will help us organize our terms in ways that will be useful to us for the autocomplete task. Let's start with the easy one, the compare_to method. So let's see a couple examples. So here I have a small text file, just like the ones we've seen before. And here I have code I can run that's just going to print out, read in and print out all of those. So here's all my terms. Now let's suppose before we print them, we go through and sort them. If I do this using arrays.sort, well, what we'll expect to happen is now they should all come out in the order determined by the compare_to method of term. Now if we look here, it looks like they're all in alphabetical order, and indeed that matches our API here. So that means someone, maybe me, must have implemented the compare_to method correctly. We may not always want to compare our terms in alphabetical order. For example, we saw earlier that after we found all the things that start with Planet, we'd like to sort them by their weight in reverse order so that Planet of the Apes 2001 ends up at the top. So how do we do that? Well, that's where this reverse weight order comparator is going to come into play. So let me just give a vague example of what we're doing here. What we really want to do is, instead of sorting by alphabetical order, as will happen by default here, we want to tell arrays.sort, hey, we'd like you to use weight instead, but backwards, right? Now, of course, Java won't understand that in English, so we need some way to specify to sort a new way to do comparisons. Now, in some languages, you can actually provide code as an argument to this function, but we cannot do that in Java. So instead, what we're going to do is create something. I'm going to call it RWO. So it's a comparator. It's a thing that can compare terms. And what is it? Well, it's going to be an instance of a reverse weight order and we will create this object, this comparator. And if we recompile and run our code, we see things come out in reverse weight order, like magic. Now you might still be asking yourself, but wait, what exactly is a comparator? Let's look under the hood just a little bit to elucidate this. This is a bit of a repeat of the lecture, but bears repeating. So here we have created a comparator, and we have passed it to arrays.sort. So what is a comparator? Well, it's a class like any other class we've built before. In this case, if we look at its signature, it contains a single method called compare. And what's a little different about this class here is it contains no instance variables whenever you implement it. It's just a container that only has code in it. So how does it get used? What is going on exactly? Well, let's imagine we live in a terrible world where insertion sort is the system sort. So here's our insertion sort code. And in this case, the sorting algorithm takes a set of objects to be compared. And then here is a little description, if you'd like, of how it should be doing the comparisons, like how we typed in use weight but backwards. This comparator is acting to do that. So here, when the insertion sort's trying to decide whether or not something is less than another, it's going to lean on our comparator object. It's going to ask it, hey, comparator, which one of these things is less? How does comparator do that? Well, he calls his compare function, which you are going to write. So it's really all that's going on. I'm not going to say anything about why here it's object as opposed to some kind of generic. If you'd like, you can go back and check out the lecture stuff, but this is fundamentally what you're doing. Comparator is just acting as a container that holds this compare function so that a sort can do its job. This brings us to our final comparator, prefix order. So it's a simple enough idea. It's a comparator that takes two terms and compares them only on their first R letters. So let's see a concrete example, and I think it should become very clear. So let's suppose we are now working with these two terms. This is the same code we were looking at before. So term 8 is jam jar, and term 9 is jar of jam jars. Let's use the prefix order comparator to get a feeling for what's going on. So let's create a comparator of terms called, let's call it prefix comp. And it's going to be a new prefix order, and we have to give it a parameter, let's say 1. And then we might ask, hey prefix comparator, could you compare for me terms 8 and terms 9? So what this is going to do is use this comparator right here to compare these two terms. Now it's comparing these two strings only based on their first character, j, and so we see that the comparator returns 0, saying that these two strings are equal up to that first character. Now suppose we change this to 3. What's going to happen now is it's going to use these first 3 characters. So if we rerun it, what we get is -1, because jam comes before jar in the alphabet. Now why would we need this strange prefix comparator? It will make sense when we get to autocomplete. So that was the term class. Next up will be binary search deluxe. Let me give a background on why exactly we want this function again. So suppose we were looking, recall, for all the movies that start with planet. We put them in sorted order by the names of the movies, and then we binary search for the earliest thing that starts with planet and the latest thing that starts with planet. So those are exactly the two functions you're going to write. Do a binary search for the first occurrence of something and the second occurrence of something. Now one thing to note is this is a very abstract function here. We're not dealing with terms in particular, but your binary search deluxe should be able to work with any kind of object. So that said, let's talk about the semantics of this class. So I would recommend that when you work on this class, you don't do it with terms. I think it's easier to think about, say, integers, and that is indeed what I'm going to do here. So in this case, what I've got is I'm going to create, in this case, a set of integers, 10 through 70. I have to convert them to capital I integer objects, otherwise arrays.sort won't know what to do with it. So that's a slight annoyance. I'm going to, in my case, I've created an integer comparator, because binary search, whenever you do binary search, you're constantly having to compare objects, right? So you need some way to do that comparison. So I'm doing it with this integer comparator. So it's listed up here. It's very simple. And so once I've created these, this list of integers here, what I'm going to do is I'm going to sort them and make sure they're in sorted order because it's very, very important. If your code starts doing weird stuff, it's probably because you forgot to sort before you did binary search. And so once I've got everything in order, I'm going to call my binary search deluxe class, and I'm going to say binary search deluxe. Among all of these integers, tell me where the first 30 is. Okay, so let's run this, and presumably it will work. Okay, so we run it, and it says 3. So we count off 0, 1, 2, 3. It seems to have worked correctly. We can also ask for the last index of something. And in this case, it says 5. So 3, 4, 5. Okay, so that's all binary search deluxe is supposed to do. But the very important thing is that it has to do it in logarithmic time. On that point about logarithmic time, I strongly suspect some of you may be tempted to do the following with this class. So let's look back at our list of movies. You might try and binary search for any instance of the word planet, and then scan slowly until you get to the beginning. But if there are lots and lots of matches, let's say you push the letter A, certainly there's going to be tons of things that start with A, it will not be log time. Danger. Let's wrap things up by bringing everything back to that fundamental autocomplete problem. So what we did before, in our example, was we wanted to find the first instance of something that started with planet and the last instance. And this is a lot like what we just did, finding the first and the last instance of the number 30. Now the difference is, with the number 30, it was a very concrete goal. We had to find things that equal 30, whereas now we need to somehow throw away everything but the first so many characters. Now perhaps you can already see where I'm going with this, but the way we're going to do that is, instead of using string compare, we're going to use the prefix order comparator, so that when our binary search is trying to decide is planet equal to planet 51, if we use a prefix order comparator of size 6, it will say yes, yes it is. And so in that way, what we can do is outsource the trickiness of trying to figure out whether two strings should be considered equal for the purposes of binary search to the comparator itself. And we can imagine having even more exotic comparators. Maybe find the first thing that contains an instance of the letter J or something like that. And the beauty of that is, by outsourcing that abstraction to a comparator, it makes our binary search method much more powerful, so we can do things like autocomplete. All of that said, I leave it to you to glue all the pieces together and build the final autocomplete class. So before I go, a reminder that this class is all about the performance requirements. That's one of the main goals of 226, is to build efficient algorithms. So pay very close attention to these performance requirements as you go. Lastly, let me talk a tiny bit about the data sets and extra credit. We provide a number of data sets that you can use not just to test your code, but also to explore and see what kind of cool things that you might find in that data. If you find anything particularly amusing or interesting, feel free to let me know. I'd be very curious. We will also provide you an opportunity to earn extra credit on this assignment if you can supply a very large data set of real-world data. Even better is if you give us a script that grabs it from the web and puts it in a nice format. And we'll be happy to use those for future offerings of the course. And also, if you want, you can try and improve the autocomplete GUI to make it slicker or more useful. Okay, well, I hope you have fun with this assignment, and I will see you next time.